All right, so we're going to look at this assessing normality. So basically the idea here is that as we go forward in the class, there'll be times where we need to know if our data is normal or approximately normal, and the problem might not tell us that. So we need a way to assess if data looks like it's normal, or if a sample looks like it could have come from a population that is normally distributed. There's going to be three ways that we can actually look at that. One is that we'll just plot the data. So we'll just make a dot plot. We can make a stem plot or a histogram. I'm going to show you how to do the histogram, and then we'll just look at the histogram to see if it's approximately symmetric and bell-shaped. The other way we can do it is that we're going to check to see if our data follow the 68, 95, 99.7 rule. We'll count the number of observations that fall into those categories. And then the last thing that we're going to do is we're going to look at the normal probability plot. When we look at that normal probability plot, I will show you a way to how those are actually calculated. If you're interested, you don't really need to know that though. You can just, it'll be the last graph option on the calculator. Again, we'll never know if a distribution is perfectly normal if we're looking at a sample, but we'll just have to figure out, you know, is there enough evidence in favor of normality or against it, but we'll never be 100% certain, especially when we're looking at samples. And again, that normal probability plot, I'll go over in another video if you're interested. It's not important though. Alright, so the first thing that you're going to have to do, you go to the next problem. So hopefully you read the problem there. Here's some refrigerators and their capacities again. You want to type all those into your calculator into a list. So again, on your calculator, we're just going to stat, edit, and then you would type all those values in there. If you want to check the sum, so I go to second stat, math, number 5. I'm going to check the sum of list 1. And so it's 569.7, 569.7. Alright, the first thing that we're going to do, like I said, we're just going to make that histogram. So I go to second y equals. I'm going to turn that plot on. Make sure when you're at that second y equals, all the other ones are off. You don't want any other ones on. So I go to that first one right there. I'm going to go over to the histogram, leave that there. I'm going to do zoom, and then I'm going to do zoom, and then that number 9, that's zoom stat. Alright, just like before, when we trace that, so back in last chapter, we would get those weird bends, so we want to fix that. So then I'm going to go to window. The X scale is what I'm going to change. I'm just going to make that 1 instead of having that decimal. Then I'm going to hit graph. Now when I hit trace, those look a little bit better. Alright, so then when I do this, right now I'm actually going to create a sketch on my paper. So I create a sketch there, just like I did last chapter. Create that sketch. So there's my 12.9 to 13.9, and there's 2 people in that one, and then the next bar, you know, there's 6, then there's 10, then there's 11, and so on. Okay, so you can just do that. We describe it, so it's roughly bell-shaped. That means that the standard deviation is that. So just looking at this right here, that graph alone suggests to me that this data, I could probably think that all side-by-side refrigerators, their capacity would be approximately normally distributed. But there's no reason here looking at this graph for me to think that there's a skew in the original data. Alright, the next thing that we're doing here is we're checking to see if the data is going to follow that 68, 95, 99.7 rule. So when I do that, what I'm going to do, I don't know that this data is normal yet. I can't use that Z table to look up probabilities. I can't use normal CDF or inverse norm or anything like that because I don't know. I'm trying to prove that the data is normal. So I'm going to have to calculate what the X bar is and what the standard deviation is. So I'm going to go to my stat, my calc, my 1-bar stats. So then I get that for my X bar, and I'm going to use that SX. The sigma X is just the population standard deviation. It's just another way. There's a slight difference in the denominator. That's it. So if you can see here what I'm doing, so I'm taking each, so there's that 15.285, which is the mean. My SX is the 1.217. And basically I'm trying to figure out what the boundaries would be. So I'm taking the mean plus or minus 1 standard deviation, the mean plus or minus 2 standard deviations, the mean plus or minus 3 standard deviations, and I'm figuring out what those boundaries are. Okay, so I figure out what those boundaries are, and then the next thing I want to do is I want to count. I want to figure out what percent of the values are within those boundaries. There's 36 values in total. So if I count how many of these values are in this boundary and divide it by 36, I'll get an idea of the percent. If I count how many are in here, I'll get an idea of percent. There's a couple ways you can go about doing that count. Just another trick here on the calculator. If you go to stat again and you go to number 2, sort, I can tell my calculator to sort list 1. And now when I go back in here, everything is in order, so it makes it a little bit easy. It's easier for me to figure out how many values are in that interval. So like I said, all I'm doing here is I'm just counting. So I went through and I counted. There's 24 of my observations are in that interval. 34 are in that interval. 36 are in that interval. And then when I count all that, I'm dividing it by 36 because that's the total number of values. So 24 divided by 36 gives me 66.7. 34 divided by 36 gives me 94.4, and so on. So this percentage of the values are within 1 standard deviation. This percentage are within 2. This percentage are within 3. So that's pretty close to that 68, 95, 99.7 rule. So that's what I'm going to say there. All right, the last thing I'm going to do here is construct that normal probability plot. And again, I'm going to make a sketch. So when I go to that normal probability plot, I'm going to go to second y equals. I'll use the first plot again. It's the last graph right here. This is where your data is. You just pick whatever, just leave that as X. Mark is just whatever you fancy. Again, those little dots are hard to see. We hit that zoom 9, the zoom for stat, and we get this graph here. What a normal probability plot is it takes each value, so it takes each X value, it puts them in order, it figures out what their percentile is, and then it finds the z-score for that percentile. So as an example, that 12.9 is the lowest value, so that would be the lowest percentile, so that's this z-score right here. The 13.7, so it has one value below it, so it's a certain percentile, and then that's the z-score for that percentile, and so on. When you're looking at these normal probability plots, if data is going to be approximately normal, if it's going to satisfy our normal check here, we're going to see a pretty linear relationship there. We're going to see that straight line. So all I wrote down there is I just made a sketch of that. And I just said it was pretty linear, so that's going to suggest that the data is approximately normal. And then the last thing I'm going to do here is I'm just going to summarize it. So I said, yes, this data is approximately normal. Again, I'm not going to say it's definitely normal. So I'm saying here that the histogram is roughly symmetric, the data follows the 68, 95, 99.7 rule, and the normal probability plot is linear. The NPP stands for normal probability plot. Sometimes you'll see that called NQP. All right, this is just kind of showing you, if you had some different kind of data. So here's symmetric, there's a left skewed, there's a right skewed. Another thing to note that we didn't emphasize is you can just remember from first chapter, if things are symmetric, the mean and median are very close to each other, or if not even the same. When there's a left skew, the mean is lower than the median. When there's a right skew, the mean is higher than the median, okay? Just looking at how the empirical rule would work. So in this one right here, we're close to that 68, 95, 99.7. But in this one, you can see within 1 standard deviation, we're at 78.6. And this one, we're at 76.9. So this is not following the empirical rule. It doesn't look like it would because it's not that nice bell shape. When you look at the normal probability plots of all these ones, what you see here is that, so there's the symmetric one, again, is pretty linear. This left skewed one, there's more data on the right than we expect to see, so there's an uptick there. This one has more data on the left, and so there's this downtick here. You can just remember that, or you can watch another video if you're interested in learning more about that. And then you just need to do those problems. Have fun.